In the previous mini lecture, we talked about the idea that use of Java's built-in thread-safe data structures can sometimes be preferable to explicit locking synchronization. But using the built-in data structures really doesn't excuse you from still having to think about what you're doing. So this is an example, again, from the Java Concurrency in Practice textbook, looking where at an example where there was an attempt at thread safety using the atomic reference built-in data structures, but there's still a lack of adequate atomicity that causes a lack of thread safety in this program. So what this program is trying to do, it's a little bit complicated. In fact, maybe the hardest thing about this example is just understanding what the program is trying to do. So this is trying to cache an expensive operation. So the idea here is that you have some number represented by a big integer, and then you're doing some expensive operation on that number, which results in an array of numbers. And the expensive operation is here is this factor here, and the idea is that if a user, and again, since this is a servlet, this is going to be a web browser. A web browser makes a request of your servlet. You get the number that you're going to do the operation on. You check to see whether that operation is the one that's in the cache. If it is, you already have the answer, which is this big integer array. If not, you do the expensive thing, and then you set the number and you set the factors. It's not easy. It's pretty easy to see that this is not thread safe, right? So imagine that we have a state. Imagine that we have a state where you have this last number. Is set to 4. So we'll just represent that. So the last time the user, the last time the servlet got called, the operation was done on 4. And we're going to represent these last factors with the array that's done on 4, right? So this represents some array, and we'll just write this 4 in here. So the last number is 4, and the last factors is some array that was done in this calculation of 4. And we don't know what that array is because we haven't defined what the factor is, but we'll just represent this by the array of 4, right? And it's not hard to see here that in a multi-threaded environment that this example is broken, right? So imagine we have thread A here. So thread A comes in, and it checks to see, and thread A was called on 4, right? So this I is going to be equal to 4 here for thread A. Then thread A does the check and says, does I equal last number? And so that comes back as true. And now we're going to have an interleaving situation with thread B, right? And so just by bad luck, thread B, let's say that thread B is called on 5. Just by bad luck in this race condition, thread B is going to do all of its operations in between when thread A checks to see if this number was 4 and then writes the response back out. So thread A is going to write some response here. And what we're going to see is that if thread B does its operations, the response is going to be the wrong response. So just by bad luck, thread B operates in here. It comes in here. It says, does I equal last number? No, because the last number equals 4, right? So this doesn't get code. It this line doesn't get called here. Instead, we go into the else in thread B. So thread B says, okay, do the expensive thing for 5, right? So the expensive thing is done for 5, and we have this value for 5 here. And then I is set to 5, or last number is set to 5. So at this point, thread B just comes and it erases this 4 and sets it as a 5. And then the last factors is set to 5. So thread B has come and erased the 4, and the calculation that's done on the 4 gets replaced with the calculation for the 5, right? So at this point, when thread B has finished its work here, last numbers become 5, and last factors has become this operation of 5, right? And so now, because thread B did this damage, so thread B got invoked, and again, you're going to see this is the same pattern that we always see, right? That thread A executes one line of code, then by bad luck, thread B comes and messes everything up. So in between when thread A executed this line of code and executed this line of code, last factors changed from 4 to 5. So thread B now writes the wrong information back to the client. Okay. So this is just the same, right? This doesn't necessarily look the same, but this is the same problem as we saw in the previous examples. It's the same problem here. It's the same problem here. It's a compound action, and whenever you have the compound action, and where you have the compound action with bad luck in the race condition, you have one thread that needs these last numbers and last factor need to be glued together. If something happens to last number, that something has to happen to the same corresponding piece of information has to happen to last factors. Because there's lack of adequate atomicity here, that isn't true. Last numbers can get checked, and then last factors can get checked. So last numbers and last factors need to get glued together in order for this to work. Okay. Now, one way that you can force last numbers and last factors to act as one unit is, of course, with a synchronized keyword, right? So with a synchronized keyword, this entire method here is in the synchronized keyword, which means that when a client makes this request, the method gets locked, and the method is locked until the client's request is finished, and then the next client can make the request. But the book doesn't like this because, of course, you're taking what was a multi-threaded application and you're just forcing it to be single-threaded. Now, interestingly, this is the JavaScript model. Like, so a Node.js server basically has synchronized on all of its methods. JavaScript is single-threaded. So it turns out that this unacceptably, if everything that you're doing here is fast, this might actually be a reasonable solution, right? If everything that's happening here is super fast, it might be okay to only have one thread at a time if your thread is super fast. But this doesn't really seem to be the Java way, right? We're not taking full advantage of the multi-threading that Java is giving us. So the book has this really rather elegant solution that it suggests, where you have basically. So notice that we drop the atomic references here. So this is now just a big integer array, not thread safe, just a big integer array. But we make this synchronized more narrow in its scope. So basically the idea is that anytime you're looking at last numbers, you put that in a synchronized block so that it's connected to last factors, right? So if you're going to check to see last number here, if you're going to check to see last number and last factor can't change, right? Like another thread can't come and interfere because you have a synchronized block. And likewise, when you're setting last number and last factor, those are going to get set together because you have a synchronized block. So the synchronized blocks basically says this code within this synchronized block and this code within the synchronized block are mutually exclusive with respect to each other. But the important thing is that the factor, the slow thing, is not in the synchronized block. So this again, somewhat elegant solution allows the last numbers and last factors to be bound together. If one changes, the other is going to change, and no other thread can come and interfere with that because they share a synchronized block. But the slow thing, the work that you do to make this number, is not in the synchronized block. So this is a nice solution that guarantees thread safety and also allows for true multi-threaded performance.